Hello everyone, welcome to Chem 76A. Today we will begin our journey towards learning and understanding organic chemistry. So in this series, let's start with chapter number 1. Chapter number 1 is a review of main concepts learned in general chemistry. So this chapter is covalent bonds and shape of molecules. In this chapter, we will review the structure of atoms, and then we'll talk about the Lewis model. Under Lewis model, we will learn how to draw Lewis structures from the condensed structure formulas. Then we will review what are main functional groups in organic compounds, and then we will discuss shapes of molecules. We will briefly go over valence shell electron pair repulsion theory, and we will talk about how this theory explains the shapes and bond angles of molecules. We will also learn how the polarity exists and what's the difference between a polar molecule and non-polar molecule. And finally, we will talk about quantum mechanical model, and in this model, we will discuss how the electronic configuration is written, and then at the end, we will discuss what is resonance and how to draw the resonance structures of various organic compounds. Let's start by defining what is organic chemistry. According to the most simplest definition, organic chemistry is the study of compounds of carbon. Uh, One of the remarkable features of organic compounds is their ability to form millions of compounds with just carbon and very few other elements. Those few elements are hydrogen, oxygen, nitrogen, and sometimes phosphorus. Over 10 million compounds have been either identified or synthesized so far. Every day, almost 1,000 new organic compounds are identified or synthesized. Organic compounds are everywhere around us. They are present in our foods, flavors, fragrances, in our medicines, cosmetics, plastics, films, fibers, resins, paints, glues, you name it. Most of the compounds around us uh, are either organic compounds or they are derived from organic compounds. The most crucial ingredient of any organic compound is carbon atom. Carbon atom is a small atom, and it can form single, double, or triple bonds. Its electronegativity is neither too high nor too low. Um, it's intermediate in electronegativity. Because of this, it forms strong bonds or strong covalent bonds with other carbon atoms, hydrogens, oxygens, or nitrogens. It can also form bonds with some metals. Let's begin with the review of a structure of an atom. An atom contains a small and extremely dense nucleus, and this nucleus is made out of neutrons and protons. And we know that protons are positively charged and neutrons are neutral. As compared to the overall size of atom, nucleus size is negligible. It's extremely small. This picture is a little misleading. In actual reality, the size of a nucleus to the overall size of atom is as if you have a football field and you have a golf ball right in the middle of the football field. That would be an actual or more realistic comparison of the size between nucleus and the overall size of atom. But anyway, although nucleus is extremely small, 99% of mass of atom is concentrated in the nucleus. So most of the atom mass is in the nucleus. The space around the nucleus is known as extranuclear space, and In this space, electrons are found, and we know that electrons are negatively charged. The size of extranuclear space is much larger as compared to the nucleus. An atom size is about 10 to the negative 10 meter. The extranuclear space around the nucleus contains electron. However, electrons are not randomly dispersed in the extranuclear space. The electrons are found around the nucleus in specific regions, and these specific regions are known as energy shells. Energy levels, and these energy levels are also known as shells. These shells define the probability of finding an electron in various regions of space relative to the nucleus. The energy of electrons in the shells is quantized. Quantization means that only specific value of energy are possible rather than a continuum of values. Each shell can hold 2n square electrons, where n is the number of shells. For example, if we are looking at first shell, so value of n equals 1. So on the first shell, total number of electrons will be 2 times 1 squared, which is equals to 2. So in first shell, maximum number of electrons can be which can be found is 2. Similarly, if you go to the second shell, the maximum number of electrons will be 8, because 2 times 2 squared comes out to be 8, and so on. Shells are divided into subshells, and these subshells are designated by letters S, P, D, F, and so on. Within these subshells, electrons are grouped in orbitals. Orbital is a region of space that can hold 2 electrons and has a specific quantized energy. So therefore we can say that if we have a nucleus somewhere here, and around the nucleus we have shells, let's say this is shell number 1 and this is shell number 2 and so on. Within each shell we have subshells, so these would represent these areas would represent subshells. Now inside the subshells, electrons are found in orbitals. There are 4 kind of shells. So in S subshell we have only one orbital present, that's called S orbital. So there is one S orbital. So for P, there are 3 P subshells, and each of that P subshell is known as P orbital, and D has a set of 5 subshells. In the first main energy level, only one subshell can exist, and that subshell is S. In the second energy level, we can have we can have S and P subshell, and we know that each P subshell is has 3 orbitals, which is Px, Py, and Pz. And in the third shell, we have S as well as P as well as D. So third subshell will have S, P subshell as well as D subshell. So all the shells, subshells, and orbitals, they define the space around the nucleus where electron can be found. In other words, these subshells and orbitals exist because the energy of electrons is quantized. They are not randomly dispersed. We need to remember, if electron goes farther away from the nucleus, its energy is higher. So in other words, energy of electron on first subshell is lowest, and as it's going away from the nucleus, in other words, it's going to higher energy level, the energy of that electron will be higher. We know that all species or all matter or electron or anything in this world would like to have lowest energy possible. However, there is a limit of number of electrons which can be placed on every subshell. And therefore, when electrons are filled in these orbitals or shells or subshells, they follow certain principles or rules. And these rules are mainly first one is Aufbau principle, and then second one is Pauli exclusion principle, and then the Hund's rule. We'll talk about that in a while. So essentially, these rules will explain that how an electron is filled in the orbitals around the nucleus. So Aufbau principle, which means build-up principle. This principle explains that orbitals are filled in order of increasing energy from lowest energy to highest energy. So in other words, when these orbitals are filled, the lowest energy orbital, which is the first orbital on the first energy level, will be filled first. And in previous slide, we know that in first orbital, in the first energy shell, only 2 electrons can be placed. Therefore, if we have more than 2 electrons, then those remaining electrons will go to the next energy level. Pauli exclusion principle states that no more than 2 electrons may be present in an orbital. So if 2 electrons are present within the same orbital, their spin must be paired. In other words, the spin of those 2 electrons will be opposite. If one electron is spinning clockwise, then the other one will spin anti-clockwise. And finally, Hund's rule. This rule states that when orbitals of equal energy are available, but there are not enough electrons to fill all of them, one electron is added to each orbital before a second electron is added to any one of them. So in other words, remember we said that each orbital can hold a maximum of 2 electrons, but if 2 orbitals of same energy are available, so instead of pairing up in one electron and leaving the other orbital empty, the electrons will occupy both the orbitals singly first. So they would prefer to remain separated before they are forced to pair up. So let's uh, write an electronic configuration. Let's put all the principles what we have learned so far to use. Let's see how we write electronic configuration. So I'm gonna show you in really simple terms, and we'll go from there. So we said that around the nucleus, imagine this part is nucleus. So there are protons and neutrons inside the nucleus, and around the nucleus we have energy levels or shells. I'm just gonna show partially. So this is shell number 1, so it's n equals 1. Then there's shell number 2, and then shell number 3, and then shell number 4, and so on. There are unlimited number of shells, and within each shell we have subshells. And remember, we talked about 4 kind of subshells. So S, and then P subshell, and then D subshell, and F subshell. And in these subshells, the energy increases this way. So in other words, S subshell has the lowest energy, P has higher than S but lower than D, and then after P we have D subshell, and then F subshell has the highest amount of energy. In first orbital, only one subshell is, in first shell, only one subshell is present, and that subshell is S. In the second uh, level, we have two subshells present, that's S as well as P. And remember, there are three P subshells, and these are called P orbitals. So therefore we have three different P orbitals, and these three different P orbitals are they have same energy, but this P orbital, this one, is slightly higher. The energy of this P is slightly higher than this S. Okay. One thing to consider here is that we have an s orbital here as well as an s orbital here. So what's the difference between this s orbital and this s orbital, and how do we distinguish it? First, the way we distinguish these two s orbital is that we write this one as 1s. 1 represents the main energy level, so it's on the first level, that's why it's called 1s, and this one would be called 2s, and this would be called 2p. The other difference is energy. 2s orbital, because it's farther away from the nucleus and it's in the second energy level, therefore the energy of 2s is much greater than 1s. Now on the third level we have 3s, 3p, and again there are three orbitals in the p subshell, and then we have this is 3d. So there are 5 d orbitals in the 3d subshell. In the fourth we have 4s, 4p, and then 4d, as well as 4f. And there are 7 4f orbitals. So only 1 orbital, 3 orbitals, and in D we have 5 orbitals, and F we have 7. Okay, so this is the spread of orbitals, subshells, and shells around the nucleus in the extranuclear space. Now all of these are empty. So all they represent is spaces where electrons may be found or reside. In other words, we can imagine them as like a building. These are different floors of a building, and then different apartments, and each orbital is kind of like different rooms. And we can imagine electrons to be people, and buildings still exist, people may not be there. So in other words, we may not have enough electrons to fill up all the orbitals, but these orbitals still exist. For example, let's take an example of an atom, let's say sodium atom. Sodium has its atomic number is 11, so it has 11 electrons. So now all of these 11 electrons want to be as stable as possible. According to Aufbau principle, when electrons occupy these shells, Aufbau is build up. So they start from the lowest energy level. So it means first we have to fill the energy level number 1. So first electron goes and occupies up. This arrow represents the way electron is spinning. So if it's spinning, so if this is electron and it's spinning this way, arrow A represents the spin of electron. Actually the arrow is the magnetic field generated by the spin of electron. So it's north to south, and if electrons spin opposite, and then the arrow will be pointing downward, so it means the magnetic field is so if this is south to north, then it's south to north here. Okay, but that's the first electron. Okay. So we have 10 more to go. Then the next one according to Pauli's exclusion principle, if two electrons are present in the same orbital, their spin is opposite. So it means, and then the second electron will spin the opposite direction. This explains why two electrons can stay within the same orbital although both of them have the same charge. Have you ever thought about it? Both electrons are negatively charged. How come they are together? This is the reason why they are together, because when they spin, they generate magnetic field. If one is spinning one way, the magnetic field is north up and south down, and the other one is spinning opposite, then the magnetic field is opposite. And we know that the opposite poles attract each other, so that's the force of attraction which keeps these two electrons together and stable. But anyway, let's continue. So out of 11 electrons, we filled up 2 of them. Then according to Aufbau principle, remaining will have to go to the next level. In the next level, again, they will try to find a lower energy orbital and or a lower energy subshell. We know 2s is lower, so then the third electron will go here, and then the fourth one will have to pair up here, and then comes the fifth electron. Now when fifth electron comes, it will go to 2p. Now there are 3 orbitals available, and all of these 3p orbitals they have a same energy. So the next electron can according to Hund's rule occupy any of these orbitals, but by convention we fill them up in the first one. Now when sixth one goes, it will not pair up. That's according to Hund's rule. It will first singly occupy all the orbital. When all of them are filled up, then they will pair up. So that's number, so let me count again, 1 2 3 4 5 6 7 8, number 9, number 10, and the last electron will go to number 11, which is 3s. So electronic configuration is essentially when we write the address of all these electrons. Address means in which orbital they are present. So in other words, if I want to write electronic configuration of sodium, I will just count back my steps. So first I filled up 1s orbital. So electronic configuration of sodium is 1s, and then we are at 2 electron, therefore I'll write 2, so this 2 is superscript, and then next 2 will go to 2s. So after 1s we went to 2s, therefore electronic configuration is 2s2, and then we filled up 2p, and there are 6 electrons, and then 3s, there are 1 electron, and this is the electronic configuration of sodium. Electronic configuration diagram shows a pictorial designation of electrons where they are placed around the nucleus. So essentially we show the orbitals around the nucleus in increasing order of energy. So the lowest energy orbital is shown at the bottom, and then the next energy orbital, and so on. So for example, this diagram shows the energy level diagram for carbon, and as discussed earlier, the lowest energy level is 1s, and then comes 2s, and then come 2p, and carbon has only 6 electrons, so 2 of them are occupied in a 1s orbital, then 2s, and then finally the remaining 2 are in 2p. As you can see that there are 3 orbitals and only 2 electrons in 2p, therefore these 2 electrons are singly occupied instead of pairing up in the beginning, and that's because of Hund's rule. In the discussion of energy level diagrams, we represented energy of shells by drawing lines. All measurement of energy are relative, meaning that we compare an energy state to some reference state. For example, in the energy level diagram for carbon, one S level is the reference and 2s and 2p are placed higher in the energy level diagram. But but now the question is, what is energy? According to definition, energy is the ability to do work. So the higher in energy, um, higher the energy of any entity is, the more work it can perform. There are different forms of energies present in this universe, but the energy which we are going to focus on is the potential energy. Potential energy is the stored energy. Uh, the stored energy is called potential energy because potentially it can be released. Let me give you an example. So imagine if you are holding a weight or a rock or a stone higher above the ground. So more higher you take it, it will become increasingly unstable, and thus it will possess more and more stored energy. And higher you go, more stored energy it will have. So now if you let go that weight, it will derive, it will drop back to the ground. When it drops back to the ground, it will become stable and all the stored energy will be released. So that stored energy which was released will be either transferred to the ground, it may break some rocks, or it may do something else. But the point is that the stored potential energy was released when you dropped it. So in this whole exercise, what happened is that you took the weight farther away from the ground, so it became unstable, and when you released it, it dropped, released the energy, and became stable. Now we can apply the same concept to chemical structures. All unstable chemical structures will have high potential energy, and they would like to release that energy and come back to the ground level, or the more stable level. With these thoughts in mind, let's return to the energy level diagram of carbon. In the ground state of carbon, the electrons are placed in accordance with the quantum uh, mechanic principles, that is Aufbau principle, Hund's rule, and Pauli exclusion principle. So all these principles dictate that uh, dictates that electron should be filled in the lowest energy level. So thus that is the most stable form, and this form is known as ground state. Now if we place the electron in different manner, for example, instead of placing the electron in 1s, or placing the first electron instead of 1s, we place it in 2s or higher. So in doing so, the electron will have now higher energy, and this state is referred to as excited state. And keep in mind that excited states are unstable, and electron would like to go back to ground state, and when it does go back to ground state, it will release all the extra energy. So that extra energy which is released, that's the potential energy. It should be noted that the electrons in the lowest energy orbital, that is 1s, so these electrons are held tightest to the nucleus because they are closest. So the negative and positive, they have the maximum forces acting on them. So therefore these electrons are hardest to remove. In other words, if we want to remove one of these electrons from the atom and take it away, we will need extremely high amount of energy. The energy required to take, or the energy required to remove an electron from an atom is known as ionization energy. So therefore, we can say that electrons in first shell or first energy level have the highest ionization energy. As we move away from the nucleus, the ionization energy required to remove electrons from the higher shells is low. So the first ionization energy is the energy needed to remove the most loosely held electron from atom or molecule. So the most loosely held electron will be present in the farthest energy level. The physical and chemical properties of any element mainly depend on the electrons present in the outermost shell of the atom, because these electrons are involved in the formation of chemical bonds and in chemical reactions. For example, if we look at the electronic configuration of carbon, so carbon electronic configuration is 1s2, 2s2, and 2p6. In other words, if this is the nucleus of carbon and it has first shell and second shell, in the second shell we have 2s and 2p orbital. There are two electrons in the first 1s, and then 2s has 2 and 2p has 2. These outermost electrons, these electrons are responsible for all the physical and chemical properties of carbon. In other words, these are the ones. These outermost electrons are known as valence electrons. Excuse me, sorry, this should be 2p2, not 2p6. Okay. So in other words, carbon has 4 valence electrons. To show the outermost electrons of an atom, we commonly use a representation called Lewis dot structure, and these dot structures were devised by Gilbert Lewis, an American chemist. Lewis dot structure shows the symbol of the element surrounded by the number of dots, which are equal to the number of electrons in the outermost shell of an atom. The examples of Lewis dot structures are given in the next slide. The beauty of Lewis model is that it unified many of the observations about chemical bonding and reactions of elements. Lewis pointed out that the chemical inertness of the noble gases indicates a high degree of stability of the electron configuration of these elements. For example, except helium, all other noble gases has 8 electrons in their valence shell. Therefore, all other atoms interact in such a way that each participating atom acquires an electronic configuration that is same as that of noble gas nearest in its atomic number. As I mentioned, that all of these noble gases, with the exception of helium, have 8 electrons in their valence shell. Therefore, a special name is given to this rule, which is known as octet rule. Atoms acquire completed valence shells in two ways. An atom may lose or gain electron um, to complete its octet. An atom which gains electron becomes anion, and atom which loses electron becomes cation. Anion has negative charge and cations have positive charge. A positively charged ion and a negatively charged ion attract each other. This attraction can lead to the formation of ionic crystals such as sodium chloride. This ionic interaction is known as ionic bond. The second method of completing the octet is that an atom may share electron with one or more atoms to complete its valence shell. A chemical bond formed by sharing electrons is known as covalent bond. In many compounds, bonds may be partially ionic or partially covalent. These bonds are known as polar covalent bonds. As I mentioned earlier, that bonds may be partially ionic or partially covalent. So the question is, how do we estimate the degree of ionic or covalent character in a chemical bond? One way is to compare the electronegativities of the atoms involved. Electronegativity is a measure of an atom's attraction for electrons that it shares in a chemical bond. Electronegativity of various elements is measured by a scale invented by Linus Pauling. So this scale is known as Pauling's scale of electronegativity. In general, in a periodic table, electronegativity values increase as we move from left of the periodic table to right. And also, electronegativity values increase as we go from the bottom of periodic table to the top. So in other words, electronegativity within a period increases, and if we move down the group, electronegativity values will decrease. Highest electronegativity value is found in fluorine. So fluorine has highest electronegativity value, and this electronegativity value of fluorine is 4.0. As we can see in this table is that if we move across the period from left to right, electronegativity value increases, and also if we go from top of any group to the bottom, electronegativity value decreases. Metals tend to have very low electronegativity values. On the other hand, non-metals, they have relatively higher electronegativity values. We know that ions are formed when electrons are transferred from one atom, such as atom A, to another atom, such as atom B. This transfer of electron will only take place if the difference between the electronegativities of these two atoms is either 1.9 or greater. The element which is losing the electron must have the smaller value of electronegativity, and the element which is gaining the electron, such as B in this example, should have the higher amount of electronegativity. For example, in this case, sodium is losing electron to fluorine, and electronegativity of sodium is 0.9 and electronegativity of fluorine is 4.0. This difference is much greater than 1.9. So as long as, in fact, this difference is 3.1, which is much greater than 1.9. As long as the difference between the electronegativity is 1.9 or greater, the electrons will be lost completely, resulting in formation of ionic bond. So hence we can say that the bond between sodium and fluorine, or fluoride in this case, is ionic bond. A covalent bond is a chemical bond formed between atoms by sharing of one or more pairs of electrons to give a noble gas configuration at each atom. The simplest covalent bond is between two hydrogen atoms. Each hydrogen atom has one valence electron, and when they pair these electrons or share these electrons, they form a H2 or hydrogen gas molecule. In this combination, each atom has two electrons around in its valence shell, which is same as the nearest noble gas, which is helium. In this sharing of electron, large amount of energy is released, which is indicated by the negative sign. Uh, so release of energy indicates that the atoms after sharing have become more stable. As we learned earlier in this chapter, stable molecules or stable uh, atoms or entities have lower amount of energy stored in them, so they have smaller potential energy. So before sharing the electron, individual hydrogen atoms had high potential energy. After they shared, they became stable because they lost most of their potential energy. In this case, they lost 435 kilojoules per mole of energy. This energy is also known as bond dissociation energy, or BDE, because this is the amount of energy required to break this covalent bond. In the example of hydrogen molecule, the molecule becomes stable after sharing one pair of electron, or in other words, they make only one covalent bond. However, in many other situations, filled valence shells can only be satisfied when bonded atoms share more than two electrons. In these cases, multiple covalent bonds will form. For example, in case of this molecule, this is ethene, by the way, carbon-carbon atoms are sharing two pairs of electron, and in this case of ethine, both these carbon atoms are sharing three pair of electron. If one pair of electron is shared, it results in formation of single bond. When two pair of electrons are shared, they form a double bond, and when three pair of electrons are shared, they form triple bond. Although all covalent bonds involve the sharing of electrons, they differ widely in the degree of sharing. Homonuclear atoms such as H2, Cl2, O2 or F2, they share electrons equally between the two atoms. For example, in case of Cl2, the shared electron is right in the middle of two Cl atoms. These kinds of bonds are pure nonpolar bonds, or in other words, these bonds are pure covalent bonds. Many other compounds such as HCl, they share electrons in the bond unequally. So for example, in case of HCl, the electrons are more closer to Cl because chlorine has higher electronegativity. So in these cases, these are heteronuclear atoms. The shared pair will be closer towards the higher electronegative element, resulting in formation of a partial negative charge on the electron where the shared pair is closer. The other atom will get partial positive charge. This kind of covalent bond uh, will have a polar character, and these kind of bonds are known as polar covalent bonds. So we can generalize at the end that some of the covalent bonds are non-polar and some of the covalent bonds are polar. So where is the cutoff? The cutoff uh, can be found with the help of electronegativity value. As long as the difference in the electronegativity values of bond and atom is less than 0.5, the bonds will be non-polar covalent, or these are also known as pure covalent. If the electronegativity difference between the two bonded atoms lies between 0.5 to 1.9, then those bonds will be polar covalent. As discussed previously, if the difference is greater than 1.9, the bonds formed will be purely ionic. The example of polar covalent bond is shown in this slide. The polarity of a covalent bond is measured by a vector quantity called bond dipole moment. It is denoted by a Greek letter mu. Bond dipole moment is defined as the product of charge, either positive or negative, uh, multiplied by the distance which separates the two atoms. For example, if a hypothetical molecule such as AB has a distance of x and the charge is n positive on A and n negative on B, then the bond dipole moment will be n multiplied by x. The SI unit of dipole moment is coulomb times meter. However, in most cases, this bond dipole moment is reported in a derived unit called debye. It's denoted by D. One debye is equals to 3.3 times 10 to the negative 30 coulombs multiplied by meter. Value of various bond dipole moments are shown in this table. The ability to write Lewis structure for molecules and polyatomic ions is a fundamental skill for the study of organic chemistry. I'm sure you guys have already learned and know extremely well how to write Lewis structures. In any case, the guidelines to draw Lewis structures are given here. So I'm not gonna spend too much time in explaining these rules. I'm sure you're aware of it and you have used these rules to write the Lewis structures multiple times. So I'm just going to show you a few examples. This table shows Lewis structure, molecular formulas, and names of several compounds. The number of valence electrons are given in the parentheses here. Notice that in these molecules, each hydrogen is surrounded by 2 valence electrons. Each carbon, nitrogen, oxygen, and chlorine is surrounded by 8 valence electrons. Also, each carbon atom has 4 bonds, as you can see in these compounds. Nitrogen has 3 bonds and 1 unshared pair of electrons, as shown in this compound. And oxygen has 2 bonds and 2 unshared pair of electrons, and chlorine has 1 bond and 3 unshared pair of electrons. These unshared pair of electrons are also known as lone pairs. In organic chemistry, we deal not only with neutral carbon molecules but also with polyatomic cations and anions. One such example of a polyatomic ion is hydronium ion. The formula of hydronium ion is H₃O, and we know that it contains a positive charge. Now the question is, which of these atoms in hydronium ion actually bear this positive charge? Does this positive charge belong to oxygen or one of 3 hydrogens? It is extremely important that we are able to determine which atom or atoms in a polyatomic ion bears the charge. This charge on an atom in a molecule or a polyatomic ion is known as formal charge. In order to determine which atom bears the formal charge, first we need to write the correct Lewis structure. After we write the Lewis structure, formal charge can be calculated with the help of this formula. So let's try to figure it out in case of hydronium ion. Lewis structure of hydronium ion is this. Let's calculate what is the formal charge on oxygen. So according to formula, formal charge can be calculated by, so I'm going to say formal charge is equals to number of valence electrons in the neutral unbonded atom. In neutral unbonded oxygen atom, we know that it has 6 valence electrons minus, in parentheses, all unshared electrons. So oxygen has one lone pair, so these are 2 unshared electrons minus 1/2 of all shared electrons. So oxygen has 6 shared electrons around it. So 1/2 of 6 is 3. So I apologize. So it is 2 and then it's plus, sorry, not minus. So when we solve it, so it will be 6 minus 5 or equals to 1 or plus 1. So formal charge on oxygen is plus 1. So that means that this positive charge belongs to oxygen. If you calculate formal charge on hydrogens, you will see that they have no formal charge or 0. The Lewis model of covalent bonding focuses on valence electrons, and it is based on the principle that all atoms want to have a completely filled valence shell. This rule is known as Octet rule. Although most molecules formed by main group elements have structures that satisfy the Octet rule, there are important exceptions to this rule. One such exception comes from the molecules from group 3A elements, particularly boron and aluminum. The compounds of boron and aluminum, such as boron trifluoride and aluminum trichloride, they have only 6 electrons in their valence shell. These kind of compounds are known as electron deficient compounds, and they are stable molecules. They are not unstable by any mean. The atoms from the third period elements such as sulfur and phosphorus are often drawn with more bonds than allowed by Octet rule, such as compounds uh, shown here, phosphoric acid and phosphorus pentachloride. And if you count the number of valence electrons around phosphorus, you'll see that they have more than 8 electrons. These kind of molecules are said to have expanded octets. The common depiction of phosphoric acid, however, has 5 bonds, and these extra bonds are explained by invoking the use of 3D orbitals to accommodate the additional bonds. However, the use of 3D orbitals for bonding is in debate. An alternative representation that gives phosphorus in phosphoric acid and octet has 4 bonds and a positive formal charge on phosphorus and a negative formal charge on oxygen. In this Lewis structure, the octet rule is still followed, and it explains the structure is using the Lewis formula. Similar explanation has also been proposed for the compounds from sulfur, as shown here.